Today I'll give a quick overview of the DART system for the benchmarking of DAA algorithms. Here I'm running DART on an Ubuntu workstation. I've begun by opening 4 terminals to run the different components. First of all, because we're in Ubuntu and on Linux, I've had to start Unreal Engine using the command line, which I have done. This opens the Unreal Engine editor. Here you can see the scene which we've created, which is just basically a texture on just an empty ground plane, and I've imported the 3 models we'll be using. So this project, on the GitHub repo, there will be a further tutorial video on how to actually set up a default project to get to where we are here. But for the meantime, for the purposes of this video, is just to give a quick run through of the system working. For the purposes of starting Microsoft AirSim with the default vehicle, in your user directory under Documents, AirSim Settings, you should find the settings.json file. In this case, we have set this up for software in the loop only, using the default drone within AirSim. So this wouldn't be using any external hardware on the table or anything like that. This is really for researchers who you don't have any hardware kit and you just want to get the system up and running quickly. So just to run through this file quickly, in this particular example, we're using a few different models. These can be built basically from the default Flying Pawn model which comes with AirSim, and there's a quick way of copy and pasting that and swapping the 3D model over to create these, which I'll show in another video. But for the purposes here, we have used 2 different vehicles, and again the AirSim Git pages describe what all these parameters are, but for the purposes of what we're doing here, I won't give it any further explanation. So if I go ahead and start AirSim on Unreal Engine using the editor here, we should see the default project come up. So this is a slightly older file here because I have to save this one, so you'll see 2 helicopters and 1 Cessna light aircraft. So to discuss, this is where the default AirSim ends and where DART begins. So I'll talk through the kind of setup configuration for how I'm going to run this project. We have a small setup.json file which we have within the DART repository. Again, this can be extended fully. When we started kind of thinking about what contents this file would have, it was kind of built around a series of scenarios, but for the limited nature of our project for a few weeks, we just looked at the one kind of direct collision scenario. But essentially, you know, as the kind of DART project grows in the future, you know, we would put configuration files here for any number of scenarios. So the one scenario here that we have thought about is a single collision with 1 aircraft. So we've put some configuration parameters in here for where that aircraft should start and end in a collision course, what speed it should go, and different approach vectors going around the kind of positions of clock essentially, and one going directly at it. This is essentially a 3D coordinate system which can be described in this Wikipedia page here. The next sim file I'll talk about quickly is, let me have a look, I'll come back to these in a minute. Essentially, when we run a simulation in DART, all we're looking to do is take control of the virtual aircraft using the AirSim API, which is essentially what this benchmark program here, RunSim, is all about. So just to maybe just look at this in the highest level, once we load in those parameters and distances for where we're going to fly our virtual aircraft to start a collision, once all that's loaded up, we go to this class method start, where essentially you can see we're moving the virtual aircraft to a set position and stopping them, and then we're sleeping for a little bit to let any sort of movement settle, because these aircraft have kinematic models. They're not static 3D models. So as you would expect a real aircraft to kind of move in 3 dimensions and move around a little bit and have some sort of feedback from when it reaches its point, that's exactly what these do, which can cause a little bit of issues on obviously detect and avoid algorithm detecting movement as the aircraft settle. I'll discuss that in the simulation. So once these are all settled at their starting positions, we would then begin the approach collision scenario, which is what we see here in these methods. So essentially what we're trying to do is just smash the pawn aircraft, we call it, into the virtual drone. So what we have here is just a loop running, going around looking at the distances to basically monitor the approach. One thing I maybe should have mentioned here as well is that we start our detect and avoid algorithm, which I'll talk about in a bit. And this loop is essentially just running around in real time, checking if a collision has been detected by the DA algorithm, and also monitoring the distance until collision happens, at which point the code will assign whether or not the detection has been detected, it has been missed, or a false alarm has been triggered, which then gets written to an output file. So this window here just shows you quickly what that output looks like for a simulation we done earlier in the project. The output file essentially writes either 1 for correct detection, 0 for misdetection, and -1 for a false positive. So in this case, for the Cessna under study for the particular algorithm, we can see here the approach vector is also noted, and then the final piece of code here, once we have these results, show results, is basically just looking at this file and pulling out the final numbers, which I think I've ran earlier here, so we can see we have 100% accuracy, no misdetections, no false positives, and the average range of detection for the aircraft was around 23 meters. So finally, taking a look at one of the detect and avoid algorithms, again, because this was kind of basically a quite low TRL level project, there's still a lot more work on how the best way to configure everything is, but there's a few variables left in our setup here where we need to write things manually. So in this case, we can see we have a parameter here just in the header file to import optical flow detect and avoid, because that was the particular the particular detect and avoid algorithm we were using in this case. So just to take a look at that, if I open that file up, the 2 algorithms that we wrote in this project were an optical flow based algorithm and a tracking based algorithm. So if I just talk about that quickly. So for the optical flow algorithm, essentially what this is doing is reading frames out of Microsoft AirSim and then processing those frames. So that's all this code is really doing. In this case, for optical flow, we're using a few of the OpenCV modules to calculate the optical flow and look at the different angles, essentially in a vector map we have of the images. And then based on the opposite direction of we see the flow or the movement with the images, we're assigning an avoid maneuver in the opposite direction. So here we have some avoid maneuvers to move down to the right, left or up, or if nothing's detected, simply the system's waiting. So that's just a breakdown of a quick breakdown of what a detect and avoid algorithm would actually look like. So anyway, getting to the guts of the problem, let's do a demonstration. One thing I didn't I didn't note here, but again will be in the documentation, is that we run a streaming server to get the frames, the video feed out of Unreal Engine. So once we have started AirSim, we need to start this up, and if we go to run simulation, if I start that up now, we should see the aircraft take off. So I'll just let that move through. So here we have the aircraft going to those start positions defined in the configuration file and implemented in RunSim. So this is what I mentioned, the settle period. You see the aircraft was rocking around a little bit, so we'll wait for a few seconds. It's now beginning its approach. And you see the detection was triggered. In this case, I've only run one simulation in the loop, but essentially that loop would continue to do the simulation that was seen there over and over and over and over again. But in our case, the algorithm was demonstrated as being successful and logged to the file. So that completes my overview of the Dart system. Again, this was a foundation level of work. There's several modifications that can be made to this. One of which is definitely adding your own aircraft, adding your own digital model here. This is something that I chose not to provide in the project because most of these assets are licensed and we can't distribute someone else's work. So it's really up to the end user to build their digital twin, digital environment within Unreal Engine, and Dart is providing the scripting to go about doing these simulations on detect and avoid algorithms. Likewise, our project Dart has implemented 2 detect and avoid algorithms. These were pretty basic, just using OpenCV functions. Really, the kind of golden goose, I guess, within detect and avoid is the use of deep learning, which would be considerable amount of work to go and train models to do so. They're going to be quite specific to terrain and aircraft, etc. But this is an ideal environment to get training data from. The AirSim documentation gives a lot of examples on how AirSim can be used to essentially take snapshots of aircraft from different positions to build up a deep learning model. So that is definitely a future area of work for Dart in the future. Thank you.